In terms of calculating money, you're right, it would stop. There's a certain point where it almost becomes too ridiculous to calculate these things anymore. But what about that number? What's going on with that number?
Me?
Yeah.
Which number?
As x gets bigger, what's going on with this number? Is it increasing at a similar rate? Or is it slowing down almost?
It's slowing down.
Okay, slowing down. Alright. Does it seem like it's maybe approaching something, but it may never get there?
Like a wall.
Like a wall. Like an asymptote. Okay. Here's what's going on with this. This process, this compounding, the question was, what happens as I compound more and more frequently with the same interest rate over the same period of time? What happens if I say compound infinitely? I just keep compounding and I never stop. So every fraction of a second I compound, and then I compound again, and I compound again. What happens? And so I said, well, let's see. We start to go this way. We start to come up with this number. Okay? Guy named Napier, guy named Euler, started recognizing these patterns. And what they said is, as we increase, as x approaches infinity of this function, 1 plus 1 over x to the x, this approaches 2.718261264590455, so on and so forth.
You just
Okay.
made all those numbers up, right?
I did not. I did not. That's actually called E. We have a name for that number. Just like pi, it's an irrational number. It never ends. It never repeats. It can't be represented by a fraction, but it's represented by E. Harry.
Is this ours? Or
That's
is it...
yours.
Okay.
That's yours. And this number, second to pi, is probably one of the most important numbers in math. It shows up in so much that we do. Nick.
So then why would you choose to have this in your bank if you never get to more than...
Well, the bank analogy works great for the compounding, monthly compounding, annually, stuff like that. But you're right. As we start to look towards compounding continuously, which is what this is called, it doesn't make sense. And banks don't do this. And some of the stuff I was reading last night, they may not even be allowed to do this because this is a really tough concept. How do you explain to your patrons that you're going to compound continuously? That you're just going to keep compounding their interest? All right? This is the maximum with which this function approaches. If we're to graph this, actually let's graph it. Aiden, can you play? If we're to graph this, we're going to look between 0 and 10,000. We're going to go, our y min is going to be 0, our y max is going to be 3.
Wait, I didn't even...
This is what our function looks like. Not terribly interesting.
What do you put in the y?
The y, we're going to look between 0 and 3.
But like, when this...
Oh, for that, I see. I just put our equation. Okay? I just put our equation. Again,
Go back to you. Oh, never mind, don't go back.
you've got it.
Yeah, we know now.
Again, it doesn't look very interesting, but in reality what's going on,
It's approaching. It's getting smaller.
it's approaching, it's not that it's getting smaller, it's approaching this line. This line, 2.718, dot, 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 dot.
That's the asymptote.
That's the vertical, or that's the horizontal asymptote that we're approaching, but we never touch.
Can you go back to the window?
Okay? It's approaching that line, but we never get there. We can always get a little bit closer than we did before, but we never actually approach it. We call that line E.
What is E? Like, is there a...
2.71826.
I know, but is E like a name?
Is it always
Spoiler.
2.178?
Okay, say what?
Is it always 2.178?
Yes. Pi, 3.14. It's always the same thing. E, when you see this notation, it's always the same thing. Carlos.
How did you memorize that?
This was a trick I learned last night. 1826, 1826, 45, 90, 45.
It's not true.
It's a triangle. Anyway, cool little trick. But, and then a 7 in front of that for good measure. Okay, so it's approaching this vertical, or it's approaching this horizontal asymptote. It's approaching that. Okay? So we've got simple compounding interest, or sorry, simple interest, we've got compounding interest, and then we've got compounding continuously. The equation for this, and now we're really going to blow your minds. And I'm going to ask you guys to put your pencils down and not write anything.
They have it on the side.
Yeah. Okay, hit the lights. Now. Yes, the math is coming. That's you need to prepare for this. Okay. And I'm not kidding about that, guys. Where we're going, I just want you guys to watch, because this is a setup of a proof to how you do this.
Wait, what is this?
Okay,
What is
so here's
this
the
equation
question. We have this. A equals P times 1 plus R over N T N T. Alright? We want to see what this equals if we take the limit of it as n approaches infinity. Does that make sense? I'm going to hold R constant, I'm going to hold P constant, and I'm going to hold T constant. But I want to see what happens as I take the limit of this function as n approaches infinity of P times 1 plus R over N to the nt. Now, let me say that again. I want to find what this becomes as n approaches infinity, as this gets bigger and bigger. We just saw that if we took all those numbers out and we left it as 1 plus 1 over x to the x, what do we get?
E.
We get e, 2.7186, or 26. Okay? Now we want to bring these numbers back in and see what formula falls out if we do some math. Now this is going to get a little weird, so sit back, relax, you don't have to write anything. You have to watch. Okay. Now, we're going to involve something called a natural log, and I don't expect you guys to know what it is, but the short of it is, Angela, the short of it is, it's an operator. I put a number into this function, a number comes out of it. So what we're going to do is take the natural log of a equals the natural log of the limit as n approaches infinity of p times 1 plus r over n to the nt. Let's see what we just did. Did I do the same thing to both sides? Did I take the natural log of both sides?
Yeah.
Forget what it means, it doesn't matter. If I do the same thing to both sides, is the equation still valid?
Yes.
Okay, that's important. Now, what you guys don't know is I can switch some things around. I'm going to rewrite this as the limit as n approaches infinity, but I'm going to bring the natural log inside here. And I'm going to say the natural log of p times 1 plus r over n to the n times t, and I'm going to call that. All right. How about this? Because I'm already looking at you guys going, what the heck is going on?
No.
Do you guys want to keep going this route? Do you actually want to see the math?
No.
Yes.
How about this? There's the math. So, math happens. We get an equation. A equals P e to the RT.
PE.
Compounding continuously.
I have PE. I hate this room.
P e to the RT. Okay? This you do need to know. Forget about all this. You need to know this. So we have two equations here. When we're compounding on a fairly regular basis, quarterly, annually, monthly, whatever. In a situation where we're compounding continuously. Is it useful in banks? No. But there's other applications in natural sciences where this does come up. If you have a large enough population set, then you can look at the birth rates. And you can almost approximate with something like this. And we're not talking replicating bunnies. Okay? Self-replicating bunnies. We're not talking about those. We're talking about a large population, say a few billion people. You can start looking at this and modeling it this route. Okay? The key points being, We have a horizontal asymptote, a line that we get close to, Martha, but we never touch. It's defined as 2.718, blah, 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 blah. It's E. We've got a model so that we can compound continuously. The most advantageous amount that we can compound, despite the fact that it's trivial, it's still the best way we can go forward. But it also models things in real life. Ryan?
So to solve this, like when we were solving equations with, like using pi, would you just, is there like a certain number that you would plug in for E?
Your calculator actually has a button, it says E on it.
But like if we were doing it on paper, we would just do like
E.
2.0.
You just write E, just like pi. In fact, this natural log thing is, have you guys seen logs?
Lost? What?
Logs. Nope. Okay.
Like reading logs.
No, logs are basically, well, it doesn't matter. Natural log is a log base E. It's a number that shows up in here. It's so special that we give it its own name, natural log. Okay? So, if you guys haven't seen that, that's okay. This is the equation that we come away with if we need to compound continuously. So we have simple interest, compounding interest, and compounding continuously interest. 3 equations that you need to know. The one we talked about last week, the one we talked about today, and the other one we talked about today.
Oh, that's.
That's those 3.
What does E mean?
E's at 2 point
Oh, yeah.
blah 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 blah.
Okay.
Wait, what is compounding?
Compounding's used in pretty much any other
I know,
case.
but like what is that one up there that you just squared? What is that called?
Compounding.
Just compounding.
Compounding interest. So let's summarize all 3 of these on the board so you guys can see what we're talking about.
Wait, what is the isn't it?
I just asked that.
Okay. So, simple interest. Meaning, we have interest rates that are once per year. We get our accounts that are compounded once a year. Simple interest. I'm going to use the same notation across all 3. A equals P, 1 plus R to the T. Okay? So it compounds 1 time per period. Compounding interest. A equals P1 plus R over N T. Compounding interest. Compounding continuously.
It's like a pirate. Arr.
A equals P-E-R-T.
Should we write this down?
I would say this is a good summary. Yes. Because your homework tonight is going to cover these 3 things.
Oh, yeah.
Wait, we're not gonna turn it in, right? We're just gonna.
We'll look it over tomorrow. Every day this room starts out really nice and organized. No. Nope, not your fault. Here we go.
And why?
Nope, that's not it.
Wait, was it the stuff I hole punched?
Yes,
Oh no,
I set it on your desk.
I know you did.
I still don't get how you do compounding continuously.
Okay, well, you're not going to actually have any of those in your homework tonight. We'll talk about that more tomorrow.
Okay.
Yeah, I was going with that.
Huh?
Oh, it's
Did you lose our homework?
Apparently.
Yeah.
Yes!
No, I bet I'll find it. Oh no. Okay, if you guys want to start putting your stuff away for right now, that's cool. And then I will find your homework the last possible second.
Sydney,
I didn't think you take the
Oh,
binder.
come on, babe, did you?
Your Lord, please help us stand up.
let's all
Oh, I'm feeling good. All right. Okay.
I'm having a heart attack. Son of a bitch. I'm allergic to homework.
You're not allergic to homework.
Jeez, I can't have
Megan, I should have said we get out of this class.
Is that still on?